Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some topical past paper questions on the topic of astronomy and cosmology for Cambridge A-Level Physics. Now, I'll leave a link to these questions in the description below, but as you know, if you looked at Papa Cambridge, there were no questions or topical past paper questions for astronomy and for medical physics. And so, like I did for medical physics, I put together these questions on astronomy and cosmology from more recent exams. And you can use them as you did with the other questions to prepare for your paper 4 exam, which will be happening soon. So download the questions, work with them, and then use these videos as a guide if at any point you need assistance. But you'll see that at some point the questions do become slightly repetitive, so at least we will be dealing with most of the concepts, if not all the concepts, and some of the problem-solving techniques that will help you in the exam. So today we'll be doing questions 1 to 4. Altogether there's 8 questions. In the next video I will put together the solutions for questions 5 to 8. And the first question, number 1, is, again, the subject code is 9702 for A-Level Physics. It comes from the winter 2023 exam, which is October-November 2023. It's question paper 4, variant 2, and question number 10 from that paper. And we are told to state Wien's displacement law and identify any symbols that we use. So we don't have to actually use the mathematical symbols. I think the words, we have enough words to explain this. But you could use an equation and then explain the symbols in that equation if you find that a better, easier way to remember the law. But basically, and I'll write down the equation afterwards, but I don't need it. The thermodynamic or the absolute temperature, which is basically the same thing, the thermodynamic or the absolute temperature of the surface of a star, we'll stick to the star, of the star's surface is inversely proportional to the wavelength at which the maximum emission rate occurs. Or you can say the thermodynamic temperature of the surface of a star is inversely proportional to the wavelength that emits at the highest intensity. So something to do with the rate at which photons of that wavelength are being emitted. The highest intensity, if I pick off that wavelength is inversely proportional to the surface temperature of the star. So quite a powerful law. So the thermodynamic temperature, if I were to write this off, a star's surface is inversely proportional to the wavelength at which the maximum emission rate occurs. So just be very careful how you word this. It wouldn't be correct to say that the thermodynamic temperature is inversely proportional to the wavelength emitted by the star, because the star is going to emit a spectrum of wavelengths, but it's going to be inversely proportional to the wavelength that comes out the most, the wavelength of light that is emitted the most. If the star appears blue, then most of the wavelengths are blue wavelengths. If the star appears orange, then most of the wavelengths are orange wavelengths. And so that's where the maximum emission rate occurs. And so basically, essentially, the color of the star will tell us what the temperature of the surface of the star is. And in symbols, it'll be lambda max, or we can simply say lambda, proportional to 1 over T, or inversely proportional to the thermodynamic temperature. For question B, we are told that a cosmology student observes the electromagnetic radiation received from a star in a galaxy. The student uses Wien's law to estimate the surface temperature of the star, a standard candle to estimate the distance to the galaxy, and the Stefan-Boltzmann law to estimate the radius of the star. You can see we put all those laws together and we can actually tell a lot of information about that star. The student observed that the radiation from the star is redshifted, and we are first asked to state what is meant by a standard candle. So we know that a standard candle is anything that we know the luminosity of. So I'm simply going to say it's an object, or I can say a stellar object, but any object with known luminosity. So I need to know the luminosity, especially if I'm going to be using the Stefan-Boltzmann law to determine size. I need to know the luminosity of something. And if I want to compare something to something else, I need to know the luminosity of at least one thing. And so anything that I know the luminosity of, such as some supernovae or Cepheid variable stars, those are standard candles. Those are things that I know the luminosity of, and then I can use those as guides to identify what the relative brightness of other things in the universe are. And so a simple 1 mark, an object with lone luminosity. Number 2 says, state the reason why the radiation from the star is redshifted. As you know, if the radiation from any object is redshifted, what this means is that if the radiation was initially yellow, it now appears to be more red. If it's blue, it might appear to be more green, etc. But basically what that means is the object is moving away from the observer. So in this case, the star is moving away from the observer. And that's because if you think about as the object is moving away, the light wave is traveling towards you. The fact that it's moving away from you means that the light gets sort of stretched out. And if the light gets stretched out, then the wavelength increases. So it appears closer to the red end of the spectrum, where the redder objects will have a higher wavelength. And so the wavelength is actually sort of stretched out because the object is moving away from the observer. So we can say that the star is moving away from the observer. And essentially what this tells us is the entire galaxy is moving away from the observer. Because if you observe any star in that galaxy, you'll notice the same thing. It's moving away from the observer. And in fact, if you look at anywhere in the universe, you'll see that all galaxies and all stars are moving away from us. So we are then told that the true values of the quantities observed or estimated are those that are corrected to allow for redshift. However, this student does not correct for redshift. So by placing one tick in each row, we want to complete the table to indicate how the observations and estimates made by the student compare with the true values. So I need one tick for each row in this table. And what I know is that the student does not correct for redshift. So whatever values the student reads is what they write down. And we want to know if the student's uncorrected values are too low, the same, or too high for different quantities, for the wavelength, the surface temperature, distance, and radius. Okay, so what about the wavelength? Is the wavelength that they estimate going to be the same as the wavelength that is actually accepted? Now, if they do not account for redshift, then what they're going to find is they see blues instead of yellows, or they see yellows instead of reds. And what this means is that the wavelength, or rather the other way around, they see reds instead of yellows, and they see yellows instead of greens and greens instead of blues. And so they take note of those wavelengths and they don't account for the redshift, and they say, well, the light from the star is green when actually it should be blue. And so they are looking at a wavelength that is actually too high. And their wavelength is too high, so they aren't actually accounting for that redshift, which means that the wavelength is actually lower from the source than what is observed. So their wavelength is too high because of the redshift. What about the surface temperature? Well, actually, let's think about what the question told us. The question told us that the student uses Wien's law, Stefan-Boltzmann law, and the standard candle to determine the different quantities. So the temperature, the surface temperature, I know lambda max is inversely proportional to the temperature, and this is a relationship between wavelength and temperature. Now we said that the wavelength was too high, so they estimated a wavelength that was too high, which means they estimate a temperature that's too low. Kind of makes sense. We look out and we see the star appearing red when it's actually yellow, actually quite hot. But when we see the red, we think that the star is cooler than it actually is, because it appears more red than yellow, or more yellow than green or blue or purple or whatever. And so we can then use the opposite identification for the surface temperature. What about the distance to the star? Well, how do I find distance? Using the idea of a standard candle, and the radiant flux intensity is the luminosity over 4 pi d squared. I'm using a standard candle, so I'm going to find the luminosity of the star that I'm going to measure, which means there's no change in my luminosity, there's no difference in my luminosity. And the flux intensity is something that's not going to change when it reaches Earth. And so the value for d will be the same, the distance to the star. And so if F and L are going to be the same, they're going to be unchanged, then D will be unchanged. So the distance to the star will remain the same. And then if I wanted the radius of the star, remember this is where we bring in the Stefan-Boltzmann law. The luminosity is 4 pi sigma, 4 pi sigma times r squared times t to the power 4. And so basically, if I want to find the radius depends here. What I'm saying, the luminosity remains the same, 4 pi sigma, all constants, but the temperature is too high, rather the temperature is too low. And so we can see that the luminosity would then be inversely proportional to the 4th power of the temperature. Obviously, if the temperature is too low, the radius of the star, or rather, not the luminosity, but I'm looking at the radius. The radius is going to be inversely proportional. The square of the radius is going to be inversely proportional to the 4th power of the temperature. So if I estimate a temperature that is too high, or too low, then I estimate a radius that is too high. So obviously I can make this R is proportional to 1 over t squared if I wanted to just take the square roots of this expression. Everything else is constant, so obviously if t is too low, r becomes too high and vice versa. So we're going to measure a radius of the star on Earth. That's not going to be correct. So you can see if we don't account for the redshift, we actually make a mess of quite a lot of the values. So this question actually expected you to apply Wien's law, Stefan-Boltzmann law, and the standard candle, the equation for radiant flux intensity, without actually doing any calculations. So it basically wanted you to know almost all of the concepts. So even though it was 8 marks, it did require a little bit of thinking. You didn't need to write the equations down, but like I always say, it helps. So overall, there was 8 marks, but it was good that it sort of challenged all of the concept, our knowledge of the concepts of cosmology. The next question, number 2, as I've numbered it, is from the summer 23 exam. So that's May, June 2023. It's question paper 4, variant 1, and question number 10 from that paper. And we are also asked to state a law. This time we are asked to state Hubble's law and identify any symbols. So if you write it in equation form, identify the symbols that you are using. But we don't need symbols. We can write it in words, just like we did for Wien's law. And we can say that the speed of recession is a good word. You don't have to use recession. Recession is the speed at which something is moving away from you or from an observer. So you say the speed of recession of a galaxy from an observer, so there must be some observation point, is proportional to the distance of the galaxy. I'm going to talk about specifically galaxy here, of the galaxy from the observer. So profound law, very old but still holds true, that the speed at which a galaxy is moving away from us is proportional to how far it is away. If it's further away, it's moving away further. It's moving away faster, rather. If it's closer, it's moving away at a much lower speed. And this is why objects that are close to us don't really have a massively observable speed of recession. But further away galaxies are moving away from us quite rapidly. So interesting, the speed of recession of a galaxy from an observer is proportional to the distance of the galaxy from the observer. I didn't really need any symbols because I didn't write the mathematical formula down. And next we are told that a star of luminosity 3.8 times 10 to the power 31 watts is a distance of 1.8 times 10 to the 4 meters from the Earth. Calculate the radiant flux intensity at the Earth of the radiation emitted by the star. So remember, radiant flux intensity F is the known luminosity L divided by 4 pi d squared, where d is the distance between the two objects. So F is what we measure at the Earth, L is what is given out at this star. And so L is 3.8 times 10 to the power 31 watts divided by 4 pi times the distance to the star, 1.8 times 10 to the power 24 squared. And what I should find is 9.33 times 10 to the minus 19 And the units, remember, is watts per square meter. And two significant figures, this is 9.3 times 10 to the minus 19. So that's not a huge amount of energy, but that shows you that at a great distance, we get very little energy from stars that are very far away. 9.3 times 10 to the minus 19 watts per square meter is something that's almost not observable, almost not felt at all by the Earth. We're then told in part C that the star in B is in a distant galaxy, and a spectral line in the light from this galaxy is known to have a wavelength of 486 nanometers. The spectral line in the light from the galaxy observed on the Earth has a wavelength of 492 nanometers. Explain why the wavelength observed on Earth is different from the wavelength that the galaxy is known to have emitted. So essentially, the spectral line coming from a galaxy, maybe it's from a star, we know the star to have a composition of maybe hydrogen, but instead of the line appearing at 486 nanometers, it appears at 492 nanometers. So the entire line spectrum is shifted towards the red end of the spectrum, shifted towards the left. And why does this happen? Well, explain why the wavelength observed is different. So we have to explain not just state. And what does it mean? It means redshift is happening, and it means that the galaxy is moving away. So the galaxy is moving away from Earth or from ours, moving away from Earth, and the wavelength is increased due to redshift. So I have to talk about the fact that there's redshift, and that's why the spectral lines are shifted towards the red end of the spectrum, higher wavelengths, but that's because the galaxy is moving away. So whenever you asked about redshift, it always means that the universe is expanding, things are moving away from other things. We're then asked to determine a value for the Hubble constant, and the Hubble constant equation is V, the speed of recession, is equal to the Hubble constant h0 times the separation between the two galaxies in question. But this is not enough for us to find the Hubble constant. And that's because we are only given the wavelengths, the wavelength observed and the wavelength emitted. And so we don't really know what the speed of recession of this galaxy is. What we can do is use the redshift equation, which says that the ratio of the speed to the speed of light at which the galaxy is moving away from us is equal to the ratio of the difference in wavelength, divided by the actual emitted wavelength, delta lambda by lambda. So what this means is that I can put these two equations together and find a value for h0. So h0 will be c delta lambda over lambda times d. Again, you could do these equations separately if you wanted. Find v over c, and then put that into the equation for v is equal to h0 d. I'm just combining it so that I can do one calculation rather than two. So this is 3 times 10 to the power 8 meters per second, the speed of the electromagnetic wave, speed of light. The difference in wavelengths is 492 minus 486. That's the redshifted wavelength minus the original wavelength. That's in nanometers, so I multiply that by 10 to the minus 9 and divide this by the actual wavelength that's emitted by the star, 486 times 10 to the minus 9, emitted by the galaxy in this case, and then multiplied by the separation between the Earth and this galaxy, 1.8 times 10 to the power 24. That's meters. And well, they specifically said it's a star. It's a specific star in the galaxy, which gives us information about the galaxy. And so if I calculate this, I get a value of h0 to be 2.058 times 10 to the minus 18 per second. Or again, two significant figures, 2.1 times 10 to the minus 18 meters per second per meter, which simply becomes a second. But you can see why they would use those units. So this question had a little bit more mathematics in it, but still it required us to understand the concept of redshift and what that means for the expansion of the universe. So this object is fair distance away, so it's moving at a rapid speed relative to us. If the star and the galaxy were closer, it wouldn't be moving away with such a high velocity. And so that question was 9 marks in total. Another interesting question. Number 3 is from the March 2023 exam. It's question paper 4, variant 2, and question number 10 from that paper. So we're told that a student observes different stars from the Earth, and we want to give 2 reasons why some stars appear brighter than others. So you wouldn't really need an extensive knowledge of cosmology to provide a reason for why you'd think some stars in the night sky appear brighter than others. So brighter stars would appear brighter because, well, firstly, they may be closer. So if I have 2 light sources and one maybe identical intensities, the one that's closer to you will appear brighter. So it could be that brighter stars may be closer to the Earth and the dimmer stars further away. But the other possibility is that the brighter stars are actually brighter. Right? So how do we say that scientifically? The brighter stars will actually be giving off more power. So we can say that if something appears brighter, brighter stars may have a greater or a higher luminosity, which is an actual quantity. It's something that we can physically measure. It's a physical quantity. So brighter stars may actually be giving off more energy, have a greater luminosity, or they may actually be closer to Earth, like any light source. So you didn't need to think too far out of the box to get that one. Next, we are told to state what is meant by a standard candle. We've already said what a standard candle is. It's any object with the known luminosity. So a standard candle is an object with known luminosity. Anything that I know the luminosity of so that I can compare other objects to it to get an apparent measure of brightness. We're then told that a spectral line from a star within a galaxy is observed to have a wavelength of 660.9 nanometers. The same spectral line measured in the lab is observed to have a wavelength of 656.3 nanometers. Show that the speed of the star relative to Earth is 2.1 times 10 to the 6 meters per second. So here, since they actually give you what the final answer should be, it's only a 1-mark question, but it's a little bit of calculation. So how do I know what the actual speed of the star is going to be? I know what the observed wavelength is, and I know what the actual wavelength when emitted by the star would be 656.3 nanometers. When measured, I only measure 660.9 nanometers. So the light gets redshifted, it's stretched out. So I know that V over C is delta lambda over lambda. So the thing I want to calculate V is delta lambda over lambda times C, which is the difference in wavelengths, 660.9 minus 656.3 divided by the actual wavelength emitted, 656.3. I can ignore the 10 to the minus 9 because they'll cancel off anyway. And then I multiply that by the speed of light, 3 times 10 to the power 8 meters per second. And what I get is, as they've asked, 2.1 times 10 to the power 6 meters per second. So this star is moving away from Earth at a speed of 2.1 times 10 to the 6 meters per second. Now we want to calculate the distance to the star, and they give us the Hubble constant as 2.3 times 10 to the minus 18 per second. Well, that's helpful because if you see the Hubble constant, you immediately think, Hubble's equation. So distance is V over h naught, which is good because we just measured V. We calculated V. If we didn't calculate it, it was given to us anyway. So we can use it as is. So it's the speed of recession, 2.1 times 10 to the power 6 meters per second, divided by the given value for Hubble's constant, 2.3 times 10 to the minus 18 per second. And what this gives us is the star is a distance of 9.13 times 10 to the power 23 meters, or 9.1 times 10 to the power 23 meters, so 2 significant figures. So that's very large distance away, as we'd expect. Part 3 says to state and explain what can be concluded about the universe based on this change in observed wavelength. Okay, so we noticed that the wavelength that we measured was actually larger than the wavelength that the star actually emitted. So what are we going to say? As always, we say that the wavelength has increased, and we must specify what the name of this phenomenon is. It is increased due to redshift. What this means that the star, and hence the galaxy containing the star, is moving away from the observer, is moving away, in this case, from the Earth. Because we are observing this all happening from the Earth's surface. So the thing we are looking at is moving away from the Earth. And it turns out that wherever we look, this is the same story. If I look in all directions, everything is moving away from us. Since we're not egocentric, the universe must be expanding. There's no reason to suggest that we would be at the center of this universe, so this would be the case wherever we were making the observation. Anywhere in the universe, things would be moving away from us. So this must mean that the universe is expanding. So when you ask to conclude something about the universe based on Hubble's law and the recession speed, etc., what you're actually saying is that the universe is expanding. So the wavelength increases, meaning this light is being redshifted. Star is moving away from the Earth, hence the universe is moving away from the Earth. The universe is expanding. Everything is moving away from everything else. So that question was worth 9 marks, a mix of mathematics and concepts, but you can see that there's maybe slightly more mathematics here than in medical physics, but you still need to understand how we conceptualize these. We try to make sense of these large distances, and we try to make sense of these very large numbers, and put them together to make some sort of estimate of the size and the temperature of things in the universe. And the next question, which is question number 4, as I've labeled them, it's the last question that we'll do for this video, is from winter 2022, question paper 4, variant 1, and was question 9 in that exam paper. And we are told to state what is meant by the luminosity of a star. So the luminosity, remember, is the total power measured in watts, but specifically it's the total power of radiation emitted by a star, if you wanted to add that in. It's not just the total power, but it's the total power in the form of radiation. So stars emit radiation. If I calculate that energy, that's the total energy. If I divide that by time, I get the total power of purely just the radiation emitted by the star. It actually does say of a star, so I can say emitted by the star for completeness. Total power of radiation emitted by the star. B says that a star in the constellation Canis Major is a distance of 8.14 times 10 to the 16 meters from the Earth, has a luminosity of 9.86 times 10 to the 27 watts, and a surface temperature of 9,830 Kelvin. They want us to calculate the radiant flux intensity of the radiation from the star observed from the Earth, providing a unit with our answer. Okay, so we've seen something like this before. We're given the distance, we're given the luminosity. Can you tell us what the flux intensity is? So again, flux intensity F is the luminosity L divided by 4 pi times the distance between the objects squared, d squared. And I know that the luminosity of the star is given as, in 3 significant figures, 9.86 times 10 to the power 27 watts divided by 4 pi times the distance of the star from Earth, which is 8.14 times 10 to the power 16 meters, and we square that value. And what we get is 1.18 times 10 to the minus 7 watts per square meter. And I could leave my answer in 3 significant figures, since my lowest number of significant figures in this calculation was 3. So that's 1.18 times 10 to the minus 7, and the units is watts per square meter. I can always just take the units of the numerator and divide them by the units of the denominator, and I can see that I will get watts at the top, square meter at the bottom, and so my final unit should be the watt per square meter. Don't confuse the units for luminosity and radiant flux intensity. They are different. Luminosity will always be measured purely in watts. We're then asked to determine the radius of the star. Now immediately, if you're asked to determine size of the star, radius of the star, you go to Stefan Boltzmann's law. And this says that the luminosity L is 4 pi sigma r squared times t to the power 4. And essentially, I have to rearrange this equation to solve for r, which is the square root. So r will be the square root of L divided by 4 pi sigma t to the power 4. Just for the lack of space, I'm just going to put the value straight into this equation. 9.86 times 10 to the power 27, which is the luminosity, divided by 4 pi times sigma, the Stefan Boltzmann constant, which will be in your data sheet is 5.67 times 10 to the minus 8 in SI units, multiplied by the temperature, 9,830 Kelvin rather, and that's to the power 4. And if we calculate this, we get a radius of 1.219 times 10 to the power 9 meters. The three significant figures, 1.22 times 10 to the power 9 meters. So that's the radius of the star, 1.22 times 10 to the power 9 meters. The last question asks us to explain how the surface temperature of a distant star may be determined from the wavelength spectrum of the light from the star. So let me show you mathematically how we would do this and then explain this in words. So if I want the surface temperature of a distant star, but I measure the spectrum, if I observe the spectrum of light appearing from the star, what I find is that the wavelength, there's a nice curve of wavelengths at different intensities. I look for the wavelength at the peak, meaning the wavelength that's being emitted by the star the most, which has the highest intensity. And what I find is that that wavelength, by the Wien's displacement law, must be inversely proportional to temperature. So what this means is if I take that wavelength and I divide it by the wavelength of some other star, then this must equal the temperature of the second star divided by the temperature of the star that I'm looking for. But the value for lambda 2 and T2 must be known. So I must use the temperature of a known star. I must use the temperature of another star that is known and then use that to compare using Wien's displacement law. Because the temperature, actually this in case, well, T1, in the case that T2 is known, then I want to find T1. So then T1 is T2 times lambda 2 divided by lambda 1. And so that's how I can use Wien's displacement law, provided I have another object of known temperature, another star of known temperature. So what I'll say in words is that the wavelength of the peak intensity, it's perfectly fine if we say the peak intensity, it's known, it's sort of understood what we mean, is determined from the star's spectrum, and then the wavelength of the peak intensity, which is now lambda 2, peak intensity from an object of known luminosity or known temperature, is determined and so once we find the two wavelengths, we are only left with one unknown, which is the temperature of the object that we are interested in. And so we can say, and we should say, that specifically using Wien's displacement law, the star's temperature can be found. Remember, Wien's displacement law, there is a constant there, but it's not a constant that we are given. It's not something that we remember either. So instead of using that constant b, which is not really a constant, a physical constant, we look for the wavelength of the peak intensity from another star, of which we know the temperature, and then we can then use the wavelength of the peak intensity of the star that we are interested in, and Wien's displacement law to find the temperature of the surface of that star. And so it's basically a matter of ratios. So anytime you need to use Wien's displacement law, you should have essentially two objects: the thing that the temperature that you're looking for, and the temperature of something else that you already know, and obviously two known wavelengths of peak intensity. And so this question really tested our knowledge of, do we know how to apply Wien's displacement law? Being able to state it is one thing, being able to use it is another. So be able to use it mathematically, but also be able to state how to use it in words if you are asked, like we saw in this question. So any of these questions are possible exam questions in this year's exam. It might be slightly more difficult or less difficult, but it's important that you don't leave this for the very last minute if you're studying, and you give it the attention it deserves, because it could very well be a significant amount of marks in the exam. As you can see, these questions were 8 or 9 marks each, which is a very significant portion of your final exam. So make sure that you're giving it the time and the effort that it deserves, just like any other topic in A-level physics. So that's the last question that I'll be doing today. In the next video, I will do questions 5 to question 8. Make sure that you are attempting these questions on your own before you're watching these videos, so you have an idea. At least you have some starting point, and then use my videos as a guide. From me, Mr. K, that's all for now, and I'll see you again next time on Everything is Relative.